Assalamu alaikum wa rahmatullahi wa barakatuh. This is the fourth video of part 1 of chapter 10, Alternating Sinusoidal Current. At the end of this video, you should be able to determine the differential equation that govern the variation of voltage in the RC series circuit during discharging phase. First, let's remember some of the concepts from the previous part. 1. Differential equation in voltage UC across the capacitor during charging is E over RC equal UC over RC plus DUC over DT. 2. The solution of the differential equation is UC equal E multiplied by 1 minus exponential minus T over tau. 3. At T equal tau, the capacitor charges 63% out of the maximum charge Qm. 4. At T equal 5 tau, the capacitor charges 99% out of the maximum charge Qm. Practically, the capacitor is fully charged and the steady state attained. To find the differential equation in voltage UC across the capacitor during discharging phase, we are going to use the following circuit, which contain a fully charged capacitor and a resistor of resistance R and a switch K. We connect the following electrical component as shown in the following circuit. Then, according to the law of addition of voltage, and by considering the positive direction as the direction of I, which leaves the capacitor from the plate M, we obtain the following relation: UMB equal UMA plus UAB. UMB the voltage across the capacitor, UMA the voltage across the resistor, and UAB the voltage across the switch, which is equal to 0 since it represents a connecting wire. So UMB equal UMA, that's mean the voltage across the resistor, that's mean the voltage across the capacitor UC is equal to RI. Then UC minus RI is equal to 0. And considering that Q is equal to CUC and I is equal to minus dQ over dt, since dQ over dt is negative, since the capacitor is discharging and the electric charges at plate M is decreasing, so dQ over dt is negative, but I is positive since it is with the positive direction chosen by us, so I equal minus dQ over dt. The minus sign is to get I in positive, so I equal minus C duC over dt. We replace the following expression in the previous equation to obtain UC plus RC multiplied by DUC over DT equal to 0. Then the equation becomes equal to DUC over DT plus UC over RC equals 0, which represent the first order differential equation that governs the variation of UC with respect to time during discharging phase. The solution of the differential equation is UC equal E, which represent the maximum voltage across the capacitor at T equals 0, multiplied by exponential minus T over tau, where tau equal RC is the time constant. And the following graph represent the variation of the function, which is a function decreasing exponentially. To verify the solution of the differential equation, we need to replace the solution, which represented by the expression of UC equal E exponential minus T over tau, and its derivative in the differential equation. We know that UC equal E multiplied by exponential minus T over tau. The derivative of this function is equal to minus E over tau exponential minus T over tau. By substitution, the differential equation becomes equal to E multiplied by exponential minus T over tau over RC minus e over tau exponential minus t over tau equal to 0. By replacing tau by RC, we obtain the following expression. E exponential minus t over tau over RC minus e over RC exponential minus t over tau equal to 0, which is equal to 0 by subtraction. Then the equation is verified. Let us study some particular values of UC according to its expression. The expression of the voltage across the capacitor is UC equal E exponential minus t over tau. For t equal 0 second, UC equal E exponential minus 0 over tau, which is equal to E multiplied by 1. That's mean UC is equal to E at t equal 0 during discharging phase. For t equal tau, UC is equal to E multiplied by exponential minus t over tau. That's mean the final value of UC is equal to 0.37 E. That's mean for t equal tau, the voltage across the capacitor is 37% of the maximum voltage E. For t equal 5 tau, UC equal E multiplied by exponential minus 5 tau over tau, which is equal to 0.007 E. That's mean for t equal 5 tau, the voltage across the capacitor is about 0.007 E. That's mean the capacitor is practically discharged. Expression of the electric current I during discharging phase. To find this expression, we are going to use the law of addition of voltage that's used in finding the differential equation of UC. UC is equal UR, and the voltage across the capacitor is equal to the voltage across the resistor. Then I equal UC over R equal E multiplied by exponential minus t over tau over R. And E over R is equal to Im, the maximum electric current traverses the circuit at t equals 0. So the expression of I becomes equal to Im exponential minus t over tau. Here we must note that the sign of the expression of I depends on the positive direction. In our case, the positive direction is chosen as the direction of I. So the expression of I is positive. But if the positive direction is chosen opposite to the direction of I, the expression of I will be equal to minus Im exponential minus t over tau, and it becomes negative. Finding the time constant tau. To find the time constant tau, we are going to find the slope of the tangent to the curve UC at t0 equals 0 using two methods. In the first method, we are going to use the expression UC E exponential minus t over tau. And in the second method, we are going to find graphically the slope of the tangent. In the first method, we are going to find the slope by finding the derivative of the function UC at t equals 0. As we know, the expression of UC is equal to E exponential minus t over tau, and its derivative duc over dt is equal to minus E over tau exponential minus t over tau. Then the value of the derivative at t equals 0 is equal to minus E over tau, since the exponential of E 0 over tau is equal to 1. And using the graph, the slope of the tangent delta u over delta t is equal to 0 minus E over t1 minus 0 equal minus E over t1. By comparison, we deduce that minus E over t1 equal minus E over tau implies t1 equal tau, where t1 is the instant at which the voltage across the capacitor UC is equal to 37% of the maximum voltage E. And as we observe in the figure, the tangent intersects the x-axis at instant t1, which is equal to tau. Summary. 1. Differential equation in voltage UC across the capacitor during discharging is UC over RC plus DUC over DT equal to 0. 2. The solution of the differential equation is UC equal E exponential minus T over tau. 3. During discharging at T equal tau, the capacitor charges reaches 37% out of the maximum charge Qm. 4. During discharging at T equal 5 tau, the capacitor charges reaches 0.7% out of the maximum charge Qm, and practically the capacitor is totally discharged. This is the end of this part. Study well and thank you for your attention.